Good evening, one and all. This is the third lecture in module number 4. Today is 3rd June 2023, and this is lecture number 24. So 2 days back we had started module number 4 in professional elective course, electric and hybrid vehicle, course 18 EC656. Today is the 3rd June, and we are going to see under the module number 4, that is electric vehicles. The topics are called as tractive effort in normal driving and energy consumption. So with this topic we are going to finish the first part of module number 4. So far we have seen in module number 4 the basics of EV. There was a block diagram which was shown to you in module number 1. Then we have seen configuration of EV. Different 6 types of configurations were there. Then there were different performance characteristics, that is traction motor characteristic, tractive effort and transmission requirement, vehicle performance and all those things. In this lecture, that is there is a third lecture in module 4 or 24th lecture overall. We are going to see 2 topics mainly for electric vehicle. One is tractive effort in normal driving, another is energy consumption. So energy efficiency and all those parameters also will come inside this. The topic is taken from Ehsani, module number 5. These are textbooks since page number 95 in the book of Ehsani. All these topics can be found out. First, let us find out what is meant by tractive effort and what is meant by normal driving of EV. So we know that there are mainly 3 characteristics for EV. Whenever I say it is EV characteristics, we actually point to maximum speed, gradability and acceleration. That means how the speed is varying, what is the maximum speed, how to accelerate the vehicle, and how the EV will act when it is climbing a hill. So what is the maximum degree or inclination that it can climb. We have seen the formula of I in the previous lecture, or sine alpha in the previous lecture. So that is called as a gradability characteristic. So we have seen what was the power capacity and what are the parameters that dictates the power capacity of the whole powertrain. That we have seen in the previous lecture. However, normal driving condition means that generally it is not climbing a hill. The vehicle is generally driving through very plain, smooth kind of a road without any gradient. Generally highway kind of driving pattern we follow in normal driving. So during most of the operation time, the powertrain operates with partial load. Partial load means the vehicle is not fully stretched with generally the energy source, with a steady energy source. The steady energy source is continuously in a discharging mode, and it is giving power for the vehicle to drive itself on flat road with high acceleration and all. That is actually called as a normal driving condition, highway driving condition. Too much of start stop is not there. So once the vehicle is started, after a long stretch it can stop. So actual tractive effort or tractive power and vehicle speed they vary widely during different operating conditions. So when the vehicle is running through the city, too much of start and stop is happening. Acceleration cannot happen much in that case. But whenever there are different driving conditions like acceleration, deceleration, uphill, downhill motion or so, these are the situations under which we can check the vehicle for different kind of capability. So acceleration, deceleration, speed, gradability, all these things can be checked. What is the pickup, how fast it picks up the actual speed. So all these things can be checked during these different driving conditions of acceleration, deceleration, uphill, downhill and all. Most important thing, regenerative braking, how it happens, how much regenerative braking energy is produced. We can check while the vehicle goes downhill. That means it is moving front and it is going downhill. So these are the testing conditions. So all these variations are associated with the traffic movement, traffic environment as well as the type of the vehicle, whether it is being driven in a city, whether it is driven in a highway traffic. All those things matters actually, because under city driving, under highway traffic driving, the drive cycle is entirely different. So different missions of the vehicles are there, because if it's a military vehicle, continuously it has to run with maybe more than 100% capacity. So in that case we can check how well the load is carried by the vehicle. If it is simple passenger vehicle, if it is simple for civilians, at that time it is being driven on the highway with without any kind of congestion or traffic problem with it. So at that time the vehicle will behave differently. So passenger cars in normal drive cycle, or military vehicle in very heavy load conditions, all those things are different cases under which a EV can be tested. It can be tested with regular operation routes, it can be tested with regular schedules, it can be tested with very abrupt kind or randomly changed schedule with unknown terrain. So all these different conditions actually helps us to understand the vehicle better. Tractive effort for normal driving of EV. So you are finding that it is difficult to describe the tractive effort. That means how much is the tractive power generated for vehicle speed variations in all actual traffic environments accurately and quantitatively. So it is not only we cannot just say it is a good vehicle, bad vehicle and all. We have to quantify it. So if it is good, how good it is while it is climbing a hill, or how good it is while it is accelerating on a highway. So that measure we should be able to do, and that measure actually can be done by means of some specific parameters or specific equations that helps us to find out different parameters or measurement parameters of the vehicle. So some representative drive cycles are already scheduled, so we can simulate the vehicle model and we can fit all these drive cycles to the vehicle, and we can check what is the driving performance of the vehicle with this driving conditions. Actually we emulate it, that's what it is said, we simulate it, typical drive environment, and we check how the simulated performance of the vehicle under different drive cycles. So some drive cycles can be suitable for city, some for highway, some for village kind of thing, some for very high traffic conditions. So there are some can be for gradient, so less gradient, more gradient. So different driving conditions are actually created or simulated, and vehicle model is actually put under this different driving conditions, which are called as drive cycles, and vehicle performance is tested before it is tested in real time. Some typical driving cycles are FTP 75 urban cycle, FTP 75 highway cycle, US 06 cycle. So all this FTP US, they are actually foreign US and UK based drive cycles. So it is mainly suited for their road. A very important thing, whenever we are designing a drive cycle, we actually define the road conditions. J22 222.7A schedule B, J227A schedule C, J227 schedule D. So all they are different drive cycles. So what is a drive cycle? It is a part of a drive cycle is shown in the right side. X-axis is generally time, y-axis is speed. So you can see here under two different timing conditions, Tk and Tk plus 1, you are finding the vehicle is accelerating because vehicle speed is increasing. So from here you can find out at Tk the velocity is Vk at this point. Tk plus 1 velocity is Vk plus 1. So we can find out the difference in V divided by difference in T. And we know that dV by dt is actually acceleration. So from the drive cycle, from the slope, we can find out what is the acceleration of the vehicle and between these 2 points. So differentiation of velocity is acceleration. We can find it out very easily from this point. So such a drive cycle is actually extended for over a very long cycle. So from there actually we can find out what are the accelerations of the vehicle very easily. So acceleration being consumed constant with a short time period that we can find out from this vehicle. So in a short time period, that is between Tk to Tk plus 1, the speed is assumed to be linear with time. So smaller is the time interval taken better calculation of the acceleration will happen. So in a short time period, the speed is assumed to be linear with time, and acceleration is constant as shown in above figure. Acceleration dvdt in a driving cycle can be obtained by, there is a specific formula, that is vk plus 1 minus vk divided by tk plus 1 minus tk. So likewise in different conditions, so in this condition you are finding acceleration is quite high. After this point you can find that the slope has changed, slope has reduced little bit. So here also the vehicle is accelerating, but not as much as between time tk to tk plus 1. After this point, which is downward slope, you are finding that it is decelerating. So vehicle is actually decelerating. So between these 2 points, initial starting point up to this point, you are finding that here also the vehicle is decelerating. So here is a formula given below towards the right side. This is y2 minus y1 divided by x2 minus x1, by which you can find out the acceleration of the vehicle. So this is a performance determining characteristics. So this you can say is proportional to the tractive effort or power generated for normal driving in EV. So in a specific drive cycle, the tractive effort of a vehicle can be expressed as Ft. So previously we have seen the equation for Pt, that is the tractive power. Whenever we are dividing tractive power by time, whenever we are integrating the tractive power, we are time integration, we are actually getting tractive force. Okay, so force is in Newton, power is in Newton meter. Power is in watts actually, that is joules per second. So whenever we are multiplying or integrating the power over time, we are actually getting how much is force. So here this is the tractive force formula for a specific drive cycle. The same formula is used, so we are going to see some 4-5 different drive cycles after this slide. Some of the names are given here at the top. So m delta dv dt. Okay, so m into a, f is equal to m into a, we know, with delta as a proportionality constant. So dv dt is nothing but the acceleration. How to calculate dv dt from the driving cycle we have seen from here. So m into a with delta is having no units. So this right side, this part is overall tractive power force generated, and this is half of rho a cd a v square. This is the aerodynamic loss, aerodynamic drag, and mgfr cos alpha. So here slightly vehicle is running on a slope of alpha. So fr cos alpha is actually the you can say the rolling resistance with some slope. So this first two terms are actually loss. Okay, and total overall force is generated, tractive force. From there, this m delta dv dt is overall force generated, and if you subtract this to losses, you are getting actual tractive force. So this formula is used throughout the driving cycle to find out how much is the tractive force generated at any instant. So it is said that this is the tractive efforts in any instant in a driving cycle. It can be calculated using this formula. Now here speed profile and tractive effort in various driving cycles and operating points are marked by plus. So you have to understand this, that is, this is a you can say FTP 75 urban. You can assume that this can be a multi-gear system, first gear, second gear, third gear, and you are finding that third gear is generally speed very high, around 80. Second gear you can say 40 to 80, and first gear you can find 0 to 20 or 0 to 40. So you are finding that it's a continuously on off kind of a thing. So this is a typical FTP 75 urban drive cycle. X-axis is time, y-axis is vehicle speed. So I can ask you a short note on drive cycle for 5 marks or so. So in that case you have to generate a image of or picture of a drive cycle like this, time and vehicle speed graph. Exactly, you don't have to remember this, but just like a case you can show a drive cycle and you can explain how it is. And you have to show in which gear actually the vehicle has operated. And below this, whenever these pluses are there, that means whenever the vehicle is speed is coming down or it is decelerating, the plus signs are given below. So it is actually regenerative. So here some points you are finding it is in the third gear. Okay, some points most of the time it is in the second gear, and a lot of time it is in the first gear. So whenever the vehicle is decelerating, speed is reducing. We know that we generally reduce the gear. So you are finding that there is frequent start stop. That's why we know that the vehicle is most of the time it could not speed up very high, so most of the time you are finding the vehicle gear is in the first gear or second gear. For very small amount of time you are finding in the first case, okay, here the speed has gone almost up to 80 to 90 kilometer per hour, between 180 up to around you can say almost up to 480 380 seconds. Okay, so 180 to 380 seconds, only for 200 seconds you are finding speed is very high. Okay, so in this case maybe the vehicle has gone into third gear. Here also the vehicle, but it has speed is not very high, so it is towards the higher side of the second gear. Speed is almost around 60. So these are the regions, but most of the time you are finding the vehicle is decelerating mode, so that is below this line. This is the zero line, you can say. So these are the pluses actually at every instant where regenerative braking is produced, and at the top these are the places where the upward kind of movement of the vehicle we are finding. So this is how the drive cycle is analyzed. So at the top there is a drive cycle simulated, and below there is a gear with respect to the drive cycle and tractive effort produced. So tractive effort in cane, first gear, you are finding almost 7 kilowatt kilonewton is produced by the first gear. Whenever the vehicle is in second gear, it is producing around 4.5 kilonewton. It is in third gear, it is producing around 2.25 kilonewton. And you are finding here, this is the region where the torque is decreasing, speed is increasing. Okay, here the speed is increasing from left to right. You can find here maximum speed is around 85 likewise. So here also you are finding maximum speed is around 85. So whatever you are finding it in the horizontal direction, the same thing is in the towards rightward direction. It is shown in this graph. So this is how the drive cycle is actually seen in case of any vehicle for a specific FTP75 urban drive cycle. Towards the right side you are finding that it is a FTP75 highway drive cycle. How do you know it is a highway? Because it is starting slowly, it is changing its gear and the speed is increasing. So speed is increasing very fast, and it has gone up to speed of 80 km per hour. That was almost third gear, and within very short time you are finding it has gone to third gear, and it is not changing its gear. There is only one place where it is decelerating a bit, and after that speed has reached just almost 100 km per hour. And after this point, after almost 750 seconds, suddenly with the vehicle is coming to the rest because it has reached its destination. So most of the time you will be finding it was ran on a smooth road. That's why you are finding most of the time the cluster of plus, they are here. Okay, so most of the time it was in the driving mode. There are only two cases when the vehicle is putting the brake, electrical brake. So this is the one case where the brake is put. That's why there are plus signs are coming below zero. So plus sign below zero means they are brake. And while the vehicle was going into rest state, there also there is some brake is pressed. So only in this downward slope and only in this downward slope, and there are very small downward slope likewise, there are plus signs below the brake. So this very big plus signs are actually here when the vehicle is actually going into rest, and this reduction in the speed is actually here. Okay, so this is just below zero because this is higher. This is in the third gear brake, and this is this one first. This is in the first and second gear brake. So from the third gear to second gear to first gear, and then vehicle stopped. Here also you are finding the same three gear system. So initial first gear is around 7 kilonewton attractive effort. Second gear is around 4.5 kilonewton. And third gear is around 2.25 kilonewton. So this is a FTP75 highway drive cycle to the right, and left side is FTP75 urban. How do you know this is urban? Because there are too much of start stop and all. How do you know this is highway drive cycle? Because there is no stopping, only the vehicle keeps on cruising and cruising very steadily. So operating points are marked by positives. So whenever you are driving the vehicle in whichever gear you are at any instant, all those things are actually tracked, and we have found out how it is looking in a real time. So this is another very diverse kind of profile which is called as US06, and here you are finding all. So in between kind of 150 up to 500 seconds, it is kind of an urban cycle. So it has gone into the third gear, even fourth gear also you are finding speed is quite high. It has reached almost speed here you can find around 130 km per hour. So whatever is shown in the vertical direction here, The same thing is shown in the horizontal direction here. So this point, if you connect below, you are finding this is around 135 km per hour. And then you are finding too much of on off kind of a thing. So all this negatives, all these brakes, they are scattered here below. So you are seeing that here brake is put in the high speed, so that brake is here in this side. So whatever brake you are putting below 0 plus means it is brake or regenerative braking, you can say. So whenever the vehicle is in high speed, from there if you are just reducing the speed, at that time your gear is high, but then you are putting brake. Whereas these brakes which are with low speed means below 50, so these brakes are actually here. Okay, so these are low gear brakes, and this brake is at high gear. So whenever the vehicle is in third gear or fourth gear, then also the brake is put. Whenever the vehicle is kind of a second gear here, then also the brake is put. And whenever the vehicle is in first gear, then also the brake is put. And in this situation, whatever rising curve you are finding, that is actually the first gear. Then whenever the vehicle is here between 150 up to 500, it is actually the vehicle is in fourth gear or top gear. In this case, you are finding the speed is very high. Likewise, so this is actually US06 driving cycle. Now another very clean driving cycle you are finding here, which is called as J227A schedule B. Here you are finding the vehicle starts, so there is no traffic at all in the road, there is no point of braking except when you want to stop your vehicle from the and you have reached almost to the destination, then only you have to decelerate. So initially it is increasing, gradual increasing. That's why you are finding that all these positives, okay, they are actually gradually increasing. So all these are actually initial gears. Vehicle never took too much of high speed, so it mainly stayed within first gear and second gear. Likewise, so this is around 30 km per hour, and then it is falling and it is falling and it is stopping. So you are finding it is started with first gear, then went to second gear, then third gear, and then again reverse, and it stopped. And for only this much period, that is whenever it was in peak speed of around 30 km per hour, from there it is falling to ground, that speed is becoming 0. So all this are shown here. So this is the brake situation, this is shown with these positives here. So this is a very clean and clear kind of characteristic of vehicle. It is given as J227A schedule B. Energy consumption is a very important thing in EV, so this will be the last topic. So 4 slides are there including this. In transportation, the unit of energy is usually kilowatt hour. So this is energy, that means whatever we call as joule, that can be given as kilowatt into hour. So kilowatt means kilojoule per second. Whenever you are multiplying it with time, it is becoming kilowatt hour. So kilowatt hour actually is similar to the joule. So rather than joule or kilojoule, it is called as kilowatt hour. The energy consumption per unit distance is kilowatt hour per kilometer, generally used to evaluate the vehicle energy consumption. IC engine based vehicle, the most commonly used unit is a physical unit of fuel volume per unit distance, such as liters per 100 km. In the United States, the distance per unit volume is fuel usually used. This is expressed as miles per gallon. It is called as MPG. L per 100 km, that means liter per 100 km. This is used kind of in Britain. In US, we use MPG. For battery powered EVs, the original energy consumption unit is kilowatt hour, measured in battery terminals, and it is more suitable. Battery energy capacity is usually measured in kilowatt hour, and the driving range per battery charge, that means once you charge the battery, how long will it go? This is actually a most important parameter in case of EV. Similar to IC engine based vehicles, liter per 100 km, that is for liquid fuels, or kg per 100 km for gaseous fuels such as hydrogen, or MPG, that is miles per gallon or miles per kilogram, is a more suitable unit of measurement for vehicles that use gaseous fuels. Energy consumption in EV, that is energy consumption is an integration of the power output at the battery terminal. So whatever power you are getting, so here is the formula for the power, how much is the output power, it is called as PB out. Velocity divided by efficiencies, traction and motor, mg Fr plus I is nothing but tan inverse of the angle, inclination angle. Fr is the rolling resistance, half this is aerodynamic coefficients, and this is actually the tractive power, tractive force. So whenever you are multiplying the net force with velocity, you are actually getting the actual power for traction. So energy consumption is actually a time integration of the power. For propelling the battery power output, so PB output, battery power output, is equal to the resistance power and power losses in the transmission and the motor drive, including the power losses in the electronics. So this is the net power, overall power generated. These are the losses, though it is actually given positive, so actually they get subtracted from this m delta dv dt and then get multiplied with v by eta. That is actually the net power for propelling the vehicle. So for propelling, the battery power output is equal to the resistance power and power losses in the transmission and the motor drive, including the power losses in the electronics. So there are a lot of electronic circuits, ECU and all. Those powers are not calculated here or considered here, but actually they also should be considered for very perfect and proper calculation. So the power losses in transmission and motor drive are represented by their efficiencies, eta t and eta m. So eta t is nothing but transmission power, eta m is nothing but the motor drive power. So these two are there. So B divided by eta t into eta m, represented by their efficiency eta t and eta m respectively. Thus the battery power output PB out can be expressed as PB out V divided by eta t eta m mgfr plus I half rho a cd af v square plus m delta dv dt. Here the non-traction load or auxiliary load is not included. In some cases, the auxiliary loads may be too significant to be ignored and should be added to the traction load. When the regenerative braking is effective on an EV, a part of the energy braking wasted in the conventional vehicles can be recovered by operating the motor drive as a generator and restoring it into the batteries. So actually they are explaining about regenerative braking. The regenerative braking power at the battery terminals can be expressed as PB in. So you can find here, this is actually PB out. This is what is called as a battery power output. So this is a battery power output for driving or for propelling the vehicle forward or for traction. This is PB in, that means power which is coming towards the vehicle. So here the non-traction load, auxiliary load, is not included. In some cases, auxiliary loads may be too significant to be ignored and should be added in the traction load. When regenerative braking is effective in the EV, that means PB in is produced, a part of the braking energy wasted in the conventional vehicles, because conventional vehicles are using mechanical braking. There actually the traction braking power is wasted, but in case of EV, we are not wasting the braking energy. Actually we are producing some energy when the vehicle is braking. So our part of the braking energy wasted generally in conventional vehicles can be recovered by operating the motor drive as a generator and restoring it into batteries. Regenerative braking power at the battery terminals can be expressed as, so PB in, alpha into V divided by eta E eta m. So everything is same here. You are finding only there is a coefficient of alpha which is multiplied. So the above formula and below formula, they are same. Alpha is just a fraction. So how much fraction of the PB out is fed back or taken back into the battery for charging? That is actually proper mathematical representation of regenerative braking. What is the formula for overall energy consumption in EV? So here the regenerative braking factor alpha is a function of applied braking to strength and the design and control of the braking system. So which will be discussed detail during electric and hybrid vehicle, and maybe in the module 5 we'll be discussing about PPS and discharge and regenerative braking more. So net energy consumption from the battery is traction time, that is PB out, plus braking. So traction is also generating energy, regenerative braking is also generating energy, and all those energy are actually outputted. So it should be noted that the braking power PB in has a negative sign. So you can find out PB in will be having a negative sign, though it is shown as positive, but this actually power is extracted from actually the PB out. So PB in has a negative sign. When the net battery energy consumption reaches to the total energy in the batteries, measured at their terminal, the batteries are empty and need to be charged. The traveling distance between the two charges, usually called as effective travel charge or effective travel range, is determined by the total energy carried by the batteries. Resistance power and the effectiveness of the regenerative braking alpha is given by this formula. So why PV in is negative? Because this is a energy generation, and here we are talking about E out. So PV in is actually not generation. PV in actually is a sorry, it is not a discharge, it is a generation. That's why PV in is negative and PV out is positive. So E out is equal to PV out delta T plus PV in delta T, traction time and braking time. Okay, so that is the integrating time, and generally PV in is a negative thing. So the same theory is explained here, and there is a final slide actually in module 4, part A, that is electric vehicle part of the module 4, because next we are going to start with hybrid electric vehicle. Here we are finding this is called as a the energy consumption graph, or you can find this as motor speed versus motor torque graph, and you are finding that this is kind of a contour kind of a thing. At the center position, this is called as a 90% efficiency area. This is the highest efficiency area. X-axis is motor speed. So this 0 to 5000, this is called as a motor speed. This can be also recalibrated into vehicle speed, that is from 0 to 200 km per hour or 0 to 180 km per hour, depending on whatever we have said previously. You can calibrate it, but you are finding that this is a kind of a hill, where the hill is having its peak between the RPM around 1000 up to actually 1600. Okay, so from 1000 to 1600. So if you are calculating in the range of 0 to 5000, so 1000 means 1/5 of it, that means around 40 kilometers, and 1600, so you can say around 40 to around 55-56 kilometers. There you are finding, so for EV, whenever you are keeping the speed, that is vehicle speed, so what I have done is actually this 100 to 1600 in the range of 5000 I have converted into 40 to around 50-55-56 kilometer per hour in 0 to 200 volt 0 to 200 kilometer per hour range. So this 5000 is calibrated to 200 kilometer per hour. That's all. We are finding that between 40 to around 50-55 kilometer per hour, the vehicle is giving you maximum efficiency. So here in the rightward side, you are finding that the speed is very high. Not necessary that when speed is very high, efficiency also will be very high. You are finding efficiency is 60%. That means here the wastage is also more. Why wastage is more? Because as you are going towards the right side, you will be finding that windage energy loss will be more. FR, that is the rolling resistance loss, will be more. So we have seen that graph, right? So that means towards the center, whenever you are finding that the vehicle is going to give maximum efficiency when the speed of the vehicle is in between 40 to around 45 or maybe 50, around that range. So this is the central part of the contour. So this is the typical electric motor efficiency characteristic. So efficiency of a traction motor varies with its operating points. Operating points are nothing but motor speed, motor torque and all. Okay, so what are the operating points on the speed torque characteristic? It is shown here in this. So there is a 2D representation of a contour. So contour representation, not 2D representation of contour, it is a 2D representation of a hill, where this 90% means peak of the hill, and as you are going towards 88, 86, 83, you are actually falling through the slope of the hill. And this is actually the efficiency determining hill of a EV with respect to the base, of you can say the motor speed, or you can say vehicle speed. So 5000 has to be recalibrated to 200. Here you are finding most efficient operating area exists in powertrain design. This area should be overlap, or at least be as close as possible to the area of the greatest operation as mentioned previously. So we are finding that running the vehicle with very high speed does not give you efficiency. Efficiency obtained in almost kind of 1/5 speed of the maximum speed. So if the maximum speed is around 200, you will be finding that around 40, 45, 50 kilometer per hour speed, if you can keep, you are going to have maximum efficiency. Maximum efficiency means the discharge from the battery, okay, will be optimized. That means the same battery will be used for longer range of travel. So this is what is the meaning of efficiency. So high efficiency means the battery with the complete charge will drive the vehicle for a longest distance. That is the meaning of efficiency. That means you are not wasting energy, you are judiciously spending the energy. That is what is meant by high efficiency. So this you have to remember, that not always high speed means high efficiency. No, not at all actually. During high speed you are finding lot of energy is wasted. But if you are driving your vehicle with 1/5 of the maximum speed, so maximum speed is 200 kilometer per hour, but you are driving your vehicle to 1/4 or 1/5, that means in between the range of 40 to 50 kilometer per hour. In that case, your vehicle will go for longest distance in one recharge. So this was all about module number 4 part A, and we have finished actually 4 lectures in this module. So we will stop here. So I think this was the third lecture actually. So we have completed the first part of module number 4, that is electric vehicle. So next lecture, we are going to start with the hybrid electric vehicle, and it will be interesting because there are many things we have to learn, how to mix the electricity with the other energy source, when to mix, how to mix, and what are the different modes of energy distribution by the primary source and secondary source. What are the constraints of the primary source, when the second source to be used. All those things we are going to see in electric and hybrid vehicle module number 4 part 2, that is hybrid electric vehicle. So till then, thank you. Good night.